And how do I steer the importance between these functions? That is, and here matRad is a little bit traditional, to not say outdated. So traditionally, you do this by weights, or that's one of the standard ways in optimization to solve multi-criteria decision-making problems. Like in radiotherapy, the problem is that you have many different things you need to balance. Yeah? On the global scale, it's two things you want to balance. The first, like you have a tumor control and normal tissue complication. It's basically, it's kind of not even radiotherapy. It's every medical treatment has a therapeutic window that lies between control and toxicity. Yes, is there a question?
Yes, we have a question. It's about the metrics. Is it the optimal dose matrix in each patient voxel, which then the software tries to come as close as possible by adjusting the beamlets, or is it already the dose in each voxel due to the beamlets calculated previously?
So these matrix that I showed earlier is for each beamlet, the dose normalized to some value. So it is not already a final plan with an intensity. It's really just some normalized value kind of for example, for particles, it could be the dose that 1 million protons deposit when they are sent in this direction. And so basically the plan is then created by using this matrix to optimize it, which can be very neatly done since you can always do matrix vector products, but that's a different story. And in the end, you end up in the system here with just kind of a dose. So you really just have like a dose cube on the CT. So this is then just one dose matrix, a dose array that stores all final dose values. And this basically dose array I can create by using the intensities that my optimizer found for each of the beamlets. You see that's 313 here, and multiplying them with this matrix. Like this matrix has beamlet dose per voxel. That's why it has number of columns of beamlets, a number of rows of voxels in the CT. Not entirely true. There's like a little bit of selection of voxels here, but I apologize. That's basically why it's so nice to use. You can just use very optimized linear algebra software, BLAS routines or LAPACK or whatsoever to do these calculations. I hope this answers the question. Okay, so where was I? Let me think. I was I think at the multi-criteria decision-making problems. You have a lot of things to balance. On the top level, this is the therapeutic window, control versus toxicity. Like basically every dose that you get right at some point gets toxic. Like if you get dose from something, at some point you are toxic. For example, if you have a different cancer treatment, let's say chemotherapy, at some point, like with too much dose, chemotherapy will kill you. But with exactly the right dose, there is a probability of controlling the cancer as well. And the wider this window is, the better is kind of the treatment. Like if you have like for example, some pill with a very wide treatment window, you can take a lot of that, or you can take a reasonable amount of that with very few side effects, then it's a very good drug. The same is true for radiotherapy treatment. If you can control a tumor with a high probability without damaging any organ, with a high probability, or like only inflict damage with a low probability, it's a very good treatment. Yeah? If you do like this treatment, which will probably have complication risk higher than tumor control, it's a very bad treatment. Yeah, kind of. And all these things, like this two pillars, are encoded in a lot of different decisions you need to make. How much dose to the tumor needs to be balanced against how much dose to the first organ, how much dose to the second organ, how much dose to the third organ. Like there's so many free variables in this problem that it's a multi-criteria decision-making problem. And one standard way to solve this from an optimization point of view is to weight all of these decisions. Like, or abstractly, it's kind of weighting decisions, and optimizations is weighting functions. So you might prioritize irradiating the tumor because you really want to have a curative treatment. And the second thing might be the toxicity on your primary organ at risk and so on. If you do a palliative treatment, this might look differently. You might not want to try to irradiate the tumor, risking very high complications if you're caring about quality of life of the patient. Yeah, doesn't make sense if the patient cannot be cured to have like a decision-making process where basically complications are with high risk and severe complications are accepted. So there's a decision-making process, and one of the easiest way to do that is just weighting functions. So you see here, the target is most important. It has the highest weight of 1,000. By the way, all of this is normalizable. So in general, you can also just take 130/10 here instead of 1,000, 3,000, and so on. But here you see target is most important. An organ at risk, like a specific region of the body which you deemed worthy enough to contour it and give it a dedicated name, is more important than the rest of the healthy tissue which will receive your dose bath, which could be fatty tissue, muscle tissue, and so on. Yeah. So this is kind of how this decision-making process is done. And so we see that what we expect is that we somehow get something around an average of 50 gray and 30 fractions in the tumor and try to get the doses below this. Since this is most important, this is what the optimizer will focus on, getting 50 gray in the target. It cannot do it. It doesn't work. Yeah. It doesn't work everywhere, but it will then find something that still minimizes the difference, the quadratic difference of all voxels to 50 gray. And it ends up with something like this for this one beam. And you can see that when looking at the dose volume histogram. Yeah, if we basically open the dose volume histogram here, yeah, it will take a bit and it will open this nice window. Yeah. This is a dose volume histogram like we saw it before. I will explain a little bit now how a dose volume histogram works. So what you see here is for each organ, for each structure that you have, you see a line. This line doesn't look like a histogram because it's not really a histogram, it's a cumulative histogram. Basically, it's not kind of counts per bin or relative amount per bin. It's basically a histogram that has kind of summed up everything from the right side. So basically you start a histogram here and then cumulatively fill it to the left. And then you get like kind of these lines. So why do these lines make sense? What is so nice, or why do we why do medical physicists and doctors like those volume histograms to analyze a plan? Like if you look on the right, to analyze this plan, you would need to scroll through all the slices and look at all the shapes of the dose you see. Those volume histograms encode surprisingly much information from a statistic. So what they show you is surprisingly easily accessible. So what a point in a dose volume histogram says, for example, this one here, which is on the outer target at 1.5 gray per fraction, it tells you that this 1.5 gray per fraction are seen by 79% of the volume, at least. This means 79% of the volume at least receive 1.5 gray. And that is some information with which you can do a lot, especially if you have these for many points. You directly know how a target should look like, if you think about it. A target should get 100% for all dose values below the prescribed dose, right? Yeah. And then at some point it should drop off because it should not have unnecessarily high doses. So targets look like this. They go like a long time with the 100 and then drop off, while organs at risk should be as much as possible in the lower left corner. So just looking at this treatment, I already see at this histogram that my core volume, my organ at risk, which is called core here, has, unfortunately, it looks kind of, to me, it almost looks more like a target because it has like a high value here and then suddenly drops down. It should be as far as possible in the lower left corner. How far it should be in the lower left corner and how exactly it should be shaped, that's empirical evidence and biology. Yeah. So for example, if an organ is perfectly serial, this means like if you hit one part of the organ, it loses all its function, and you have a reference dose for when this happens, then you just know your organ at risk needs to be below this point. Like your dose volume histogram needs to be left, all of it. If you have like certain probabilities, so for many organs, you have like kind of multiple steps. So you have only 5% of the volume should receive a dose greater than this. Only 15% of the volume should receive a dose greater than this. You have all these points directly available. Like, because a lot of organs are kind of between this parallel serial relationship, sometimes they tell you a lot about it. It's of course still too crude for detailed biological functions. There might be a specific region in your organ which is dedicated to something, a specific region with a serial, a specific region with which is parallel. But you can see a lot about the shape of these lines. Like, is it preliminarily low dosed? Is there a high dose tail? Yeah, it's very easily to see. You see, for example, in the body, of course, most of the body in this treatment basically receives no dose. You see this here, except for very tiny amounts of out of field dose. But going to higher doses, you see there is like a tail, and actually the highest dose is quite high because of these two red dots. And you directly see this here. And it's very nice if you, for example, have a hotspot somewhere, you kind of directly see there must be some hotspots here because my doses go so far out, or if you really have substantial high dose regions outside of your tumor. But what you kind of see is that our optimizer really tried to get towards these 50 gray in 30 fractions, which would be 1 2/3 of gray in 30 in one fraction. He kind of went towards this 1.66, here it's 1.61, so he didn't manage completely because there are organs that are kind of colliding with getting those into the tumor. So yeah, that's kind of a trade-off that the optimizer chose. So the optimizer doesn't really care about how good this plan is, they just find the best trade-off. So that's kind of all this. And here you also see, if you remember the clinical medical physics presentation, you see all these values. Yeah, for example, you see the D50 or D5, D95. If you remember, D95 and D5 are values, or D2 and T98, that we use as surrogates for maximum and minimum dose. Because you can think about, if you look at the maximum dose in an organ or the minimum dose, it's very sensitive. There might only be one voxel that has a very low dose, and suddenly it looks like a super bad dose because the minimum dose is super low in the target. But this might just be because this target is at the border of this voxel is at the border of the tumor, and actually due to some discretization artifacts, it lies half outside of the tumor. And basically for the plan, the dose itself for speed reasons was calculated on a different resolution, and so on and so on. And then you just have this one voxel telling you with the minimum dose that your treatment is bad. But when you look at 99% of the voxels, they all are above a very reasonable level. You want to kind of get rid of this artifact, so you use these D2 and D98, which basically throw out the kind of worst two voxels in both, 2% of voxels in both directions. So you have a more stable idea of what the minimum and maximum dose would be. So this is basically how this works. You can look at all of these statistics and see what they mean. Basically, these are also, most of those are just points in the dose volume histogram, because the dose volume histogram is such powerful in showing relating volume to dose. It's used so much in clinical treatment planning and also when you do research. Like I think in in every medical physics paper about radiotherapy where dose distributions are involved, you will see a dose volume histogram and a comparison between dose volume histograms. The standard plot that you look at in a paper is a dose volume histogram with another one from a different plan in dashed lines, and they show all the target coverage is much better and whatsoever. So that's kind of really important tool in the medical physicists and also the medical doctor's arsenal. Okay, so now we are at this plan, and I think we can really nicely finish with the photon world in this session. So as said, the idea that I said the engineer had, I do not know if the person who had the idea was indeed an engineer or what they did. Back then, probably most of them were physicists anyway, working on this topic. What we do is we can just stack beams, right, to get a nice photon treatment to avoid like this problem of having this exponentially decaying dose. We just stack beams, so we have multiple beams. And matRad, as said, is a little bit freestyling this, so at the same time very easy, and at the other time very intuitive for people who are unintuitive for people who use clinical systems. You can just write angles. And now think about like you have a 360-degree arc in a sense from which you can choose angles. I always let the people decide what they want to do. Like just choose about 5, 7, or 9 angles that you want to distribute around here. And set a plan up. So you just type numbers. I usually just, for these purposes, space 5 angles in equal distances. Yeah, it's like I know the numbers by heart now, but you can easily find equidistant angles of equal distance. So these are all 72-degree spaced angles. You just type the numbers with spaces in between them. And then for the couch angles, if this is not grayed out, if this is grayed out, you have the educational version, and it will, I think, be automatically filled. For the couch angles, you just use zeros and exactly the number of angles that you have for gantry. So as said, this is very easy to use, but very unintuitive if you're used to more user-friendly applications. But research applications are usually not user-friendly. So this will show you that you will now look for these 5-star beam treatments. So often when you have templates in a clinical medical system, they would be called 5-star, equidistant, or 7-star, because they look like stars for the people. Like these 5 beams. Like here, if you don't know how to visualize this after typing, this was the button down here, the visualize plan beams button. And of course, what we need to do now when we have these beams set up, so you can still think a little bit about what beams to set up. You can also think about it in the lunch break. Maybe you have some crazy ideas. Of course, now we need to go to the procedure again. Yeah, we have 7 new beams. These beams exist in our head. Now we need to calculate what's going on in these beams. So we go through our workflow again. We calculate the dose matrix. Yeah, and this now takes, of course, a little bit longer. You have 7 beams. Yeah, my computer, if I listen to it, gets a little bit more active. Nice, warm and cozy here.
There is a question if we can.
Yes.
Is it possible to import RT plan file from other planning system to calculate the dose in the matRad using that beam parameters?
So in principle, you can import DICOM files. So you can, what people do quite often, they import CTs and RT structs. That usually works without problems. There might be weird stuff going on. What also usually works without problem is an RT plan and an RT dose. What is tricky is an RT plan. And there's one specific reason why this is tricky. An RT plan does not contain the machine, the irradiation source data. Yeah. So it contains, an RT plan contains kind of all the steering information, like how do the, it gives you a name of the machine. Yeah, at some point it says this is a variant true beam, a Electa whatsoever, and I don't know all the names. So it will give you the name, a Siemens artist, for example. It will give you the name, but it will not tell you something about the irradiation source. So you might be lucky, it will say it's a 6 MV spectrum, but the exact physical properties of all the geometries will not be modeled there. So you can import it, but at some point it will ask you, please specify matRad's machine file for that machine. And this machine file will not match the information in the RT plan because it's just a different machine and you don't have the data exactly of how kind of the particles are transported through the linear accelerator. Yeah. So it cannot exactly recompute it. You can go through the procedure of kind of finding the machine data. Yeah, there's like, if you want, you can contact us, we can help you with that. So basically, if you have commissioning data, you can create a matRad machine to recalculate the beams, and this should work well enough for most of the cases. But it's a little bit more tricky. But then you can import the RT plan, you can do a direct recalculation of what you did before, or you can do replanning with your machine and export it back. There's actually also at the moment some discussion on GitHub ongoing about this issue, like importing machines and working between systems. So it works, and there's like some people interested in doing this a little bit more. So yeah, if you can engage in that, or you can just write us as well with the contact information there, and then we can figure this out. But in principle, it works with RT plans. Just the machine information is a bit tricky. Because machine information just requires so much data from actual measurements and geometry that is just not stored in the RT plan file. Okay, but this is now the new plan that we generated. We calculated the dose. You can have a quick look and see, like I'm done in 1 or 2 minutes, so we all get ready for lunch. We can look at our matrix again. It has more beamlets. It has approximately 5 times as many beamlets because we have 5 beams. Now 1,300 now. So this object gets bigger and bigger. It's also usually what makes your computer run out of memory. So this is now our new matrix. And now we hit optimize again. And we have the same settings. Yeah, exactly the same settings as before. Our mathematical encoding of the clinical problem is still the same on the abstract level of these functions. But now we have much more degrees of freedom to play with. And you see also that the optimizer now needs a little bit longer. Sorry, a lot of things happen just at the same time. It needs a bit longer to minimize these functions. So you see there's like some kind of decrease here that's going on, yeah, until it finds a value where the function does no longer decrease. So it takes a little bit more time. You also see here that we have, I will just delete the old plots. You also see that our shapes become a little bit more complex. We have 5 beams now, so we get like kind of these 5 shapes. This is what the collimator will look like. Like we rotate to beam 1, then irradiate all these shapes after each other. Then we rotate to beam 2. So they look a little bit more complicated, but in the end, what you have is a much nicer dose distribution that seems to already be a more sensible treatment. You have much less dose in the organs at risk. And you also see the idea forming, the more beams I have, the lower my dose in the body will be, and the more it will be conformed to the target. Because if you look at the target here, it is now nicely covered in a hot red area. You see this geometrical artifacts here, where basically you have kind of this really just geometry in a sense. It's very difficult here where these beams, because these beams overlap in certain angles, to make a round shape, so we'll have kind of these spikes that are formed due to the geometry of the beams. And if you have more beams, these will disappear and end up to form a really nice C-shaped red area. You also see that the optimizer, because our core is more important than our body, put some extra effort into reducing the dose in the core region. You see that quite nicely. Can try to get rid of the isolines. Maybe that also makes it nice to see that there is this blue zone of no dose. So if you have chosen other beams, sometimes people get overexcited and try to be very creative in how to put the beams, kind of spare some organs with the beam placement. Maybe you might have done the experience that this will now have end up in very weird dose distributions, yeah, because you didn't give enough degrees of freedom. You tried too much to limit the geometry by sparing certain areas. And sometimes the computer can just make a better decision than you on what to spare or not. Yeah. So what really often standardly is done, just create many beams equidistantly and let the computer decide. Sometimes there are some logical decisions. For example, prostate, we can look at that later. You have these two femoral heads of your femoral bone, or how they are called. And of course, it makes sense to not necessarily choose your beams in a way that they irradiate through that. Yeah, if you can avoid it easily, but just a little bit deviation on the angles, it might help you. But getting overly excited and kind of try to get them all from one direction can actually do more harm than do good. But maybe you also found a very good set of beam angles that created a perfect plan. Who knows? I do not see all your results. And as a final thing before you go to lunch, you can also look at the dose volume histogram and see how much better this looks. Like, this is how a target is supposed to look like. It could be a little bit steeper here, but you want to be at 100% until you prescribe dose and then fall down. You also see that the optimizer really managed to get this 1.66, this 1 2/3 of gray perfection now, because it's much easier to generate this dose now with these many degrees of freedom. And you also see that the organelle risk is relatively much further pushed to the left. Of course, we need to have those in the organelle risk. It's physically impossible to create this ideal distribution, but it's much better like pushed left than before. So that's kind of the first chapter on photon planning. So now you know basically how the steps work, kind of what is computed, how these functions work. We will maybe after the lunch break try a little bit changing one of these mathematical function values and then go to ions, because that's why we're here. Yeah, there's a question.
Yeah, there was a question about modeling a specific machine using beam data and matRad to add into the machine. But if you could tell more about it or insert some document like reference.
I can, I think the best for this is really, if you have some questions, like for example, you want to integrate your own machine. This is something which you can do. Like if you have like these specific questions, the best thing to do is one of three things. One thing is you can write an issue. You need an account, a GitHub account for that, and you can just write an issue. You can start a discussion on a topic. For example, there is already a discussion on photon machine integration and validation, which is a little bit short, but it links to other threads or issues where some people already did it. And the last, or like also always a thing that you can do, it's not the last thing, but sometimes I will just point you to something. You can go to, now where is our contact address? It's somewhere in the README. Here, you can just click get in touch and write us an email. And we are always happy to help with such problems, especially photon machine integration, since I'm primarily in proton and ion planning research. I do not care so much about the photon machines, to be honest, anymore. So I actually also talked earlier before. So if there's someone interested in working with the machine data, just contact us. We're always happy to have some people there that are interested in this, and then we help them. And with this, we can kind of sanitize this a little bit more, make it easier, see what the problems for the users are. So really just get in touch with us or write something on the GitHub and we can help you with that. I know it's always like, many people like it more to have some document and some resources, but so far we have not done this often to integrate photon machine data, not ourselves. And so there is nothing written down, but the more interaction we have with the users, that's kind of one of the main things of open source, interaction with the users. The more we can figure out a way to make this nice. and then also provide such a document.